In the summer of 2026, the sheer velocity of human engineering is almost difficult to process. We are now mass-producing the infrastructure of space, deploying dozens of complex machines into orbit with the routine predictability of a morning commute. Take SpaceX's Transporter-17 mission. They packed 81 separate satellites onto a single Falcon 9 rocket and fired them into a sun-synchronous orbit. It functions like a cosmic bus route, dropping off hardware precisely where it needs to go. By treating rocket launches like shared rides, the cost to reach space has plummeted. Small startups and university labs are now paying a few $100,000 to put their own specialized tech into orbit, bypassing the traditional gatekeepers of aerospace. At the exact same time we are optimizing low Earth orbit, we are pushing professional-grade processing power into our pockets. Apple's iOS 27 has introduced an entirely new computational photography engine for raw images. The software uses neural networks trained on millions of photos to distinguish natural texture from sensor noise. It allows you to run old, low-light photographs through the new neural engine, recovering fine details in the shadows that were previously considered permanent digital noise. The common thread here is that both orbital mechanics and mobile photography are being abstracted. We interact with the sleek hardware, but we rarely look at the software hypervisors and code libraries that actually manage the data. We trust that this hidden foundation is as robust as the machines it powers. This momentum has reached a peak in the capital markets. Elon Musk finalized a $1.25 trillion merger between xAI and SpaceX. By rebranding as SpaceXAI, the new entity creates a direct link between planetary-scale infrastructure and cutting-edge artificial intelligence research. The strategy is a massive vertical integration. They plan to weave machine learning directly into the hardware of space travel. That means Starlink networks that automatically optimize their own routing, and AI systems built to autonomously pilot landing modules on the surface of Mars. And the AI models they plan to use are reaching staggering levels of internal complexity. Researchers at Anthropic recently discovered that their Claude model had spontaneously developed a J-space, a hidden mental workspace inside the neural network. This follows a concept called global workspace theory. It suggests that consciousness functions like a theater. Before the model writes a word, multiple streams of information converge into a single bottleneck. The model integrates this data, considers its options in the J-space, and then broadcasts a unified decision to its output layer. We have successfully engineered digital architectures that mimic the functional structures of the human brain, and we are packaging them inside trillion-dollar interplanetary megacorporations. But underneath all of that towering ambition, the invisible backbone holding up the modern internet is quietly rotting. Security researchers just uncovered a flaw buried inside the Linux KVM hypervisor. This is the exact virtualization software that major cloud providers like AWS, Google Cloud, and Azure rely on to partition their massive servers. The bug is called Jane escape. Technically, this is a use-after-free memory error. It happens when a program tells the system it no longer needs a specific block of memory, but fails to clear the digital address pointing to it. If an attacker occupies that memory space before reallocation, they can run malicious code. In cloud computing, this lets a guest VN escape its container, hijack the host server, and gain control over every client's data. The most concerning part of Jan escape is the timeline. This vulnerability was not created by a new AI. It was a human coding error introduced in 2010. It sat in the foundational code of the cloud, entirely undetected, for 16 years. Our most ambitious networks can be entirely toppled by a single overload line of code that we've been blindly trusting for over a decade. Exploiting these cracks doesn't require a super genius. We saw this clearly with a recent attack on Gitea, an open-source platform used to manage proprietary code for thousands of organizations. Look at this authentication bypass. Attackers targeted Gitea's Docker deployments and realized they didn't need a password. They just sent a basic HTTP request with a header labeled xWebAuth user. Because the software blindly trusted that label without verification, it instantly grants full administrator access. It takes years for teams to build these robust platforms. It took attackers exactly 13 days from the moment this bug was disclosed to begin actively exploiting it in the wild. This is the harsh asymmetry of modern cyber warfare. Human defenders must protect millions of servers every second. Attackers only need to find one misconfigured header to win. The integration of our space networks, our artificial intelligence, and everyday communications is accelerating. The borders between these technologies are disappearing. We spend a lot of time worrying about cinematic threats, like a conscious AI deciding to turn against us. But the actual danger is more mundane. It is decaying memory management and forged HTTP headers. The era where software security can be a secondary thought is over. If an organization is still relying on slow, monthly patch cycles, they are already operating outside the window of defense. To survive the interconnected future we are building, our foundational security must become exactly as advanced, autonomous, and precise as the technology we are preparing to send to Mars.